Hi everyone, this is Dr. Hamilton. You might have seen me around. If not, I'm sure you'll see me around again. Now, I have to tell you, I'm making this recording for you at my house, and I have 2 dogs and a cat, so you may hear, oh, look, there's a cat here now. We may get a few interruptions, but that's okay. What we're going to do today is read this piece that your teacher has given you together. So I'm going to read it to you, and while I'm reading it to you, oh, the cat just got rid of my picture. While I'm reading it to you, I want you to get out a highlighter, and I want you to highlight some of the vocabulary words as we're talking. So let's read this together. We're going to start right here underneath where it says reflect. Has anyone ever told you to sit still? You may do as you're told, but in truth, you can never really sit still. And that's because, as you probably have already heard, the Earth is constantly moving through space. But did you know that the ground beneath your feet is constantly moving too? However, we don't feel this constant movement. Why don't we feel it? The Earth's surface is divided into plates. Our planet is made up of several layers. The top layer is the crust. The center layer is the core. Between the crust and the core is a thick layer of partly molten rock called mantle. Earth's crust and the uppermost part of the mantle together make up a layer of solid rock called the lithosphere. The lithosphere is the cool, rigid, outermost layer of Earth, and it's broken into large pieces called tectonic plates. Now let's stop there and go back and do some highlighting. I want you to highlight the words that are already bolded. You can see that I already highlighted the word lithosphere. I want you to highlight crust. This is the top layer of the Earth. Core. Here's the center layer of the Earth. We have some molten rock. Go ahead and highlight both of those. Maybe you remember hearing about that from when you studied rock, specifically igneous rock. Lithosphere, and then go ahead and highlight tectonic plates. The tectonic plates are, remember, the thick pieces of the Earth's crust. I'm going to move myself over here so we can talk about this. These tectonic plates contain different types of crust. The crust beneath the oceans is called oceanic crust, and this crust is denser than the crust that makes up the continents, which is called the continental crust. Let's take a minute to look at that picture over there. That picture here shows us a cutout of the inside of the Earth and also how thick these pieces are. So here's the lithosphere. Can you see that it's just this tiny, tiny piece here, the uppermost layer of the crust? And then you've got the mantle, which is all this piece here. That's the mantle. And then you have a liquid core and then a solid core. All right. Now, the tectonic plates contain different kinds of crusts. We already read that. The crust beneath the oceans is the denser crust. Okay. Scientists have given names to these tectonic plates. The map below shows the current major tectonic plates. Many of these plates are named for the continents or oceans they support. Maps of ancient land and water patterns show how Earth's plates have moved great distances, collided, and spread apart. So you can see the plates are broken up, if you look here, a lot like different continents are named. And here's the major tectonic plates. The African plate here, the Antarctic plate here. Look at the North American plate is huge. And you see that the plates are also under the oceans. So it's not just land, but also under the oceans. All right, now, what is it that moves these tectonic plates? Well, that's convection currents. Convection currents move tectonic plates. Just below the lithosphere is a shallow layer of mantle called the asthenosphere. Here's another huge science word for you. The partially molten rock in the asthenosphere slowly flows due to a process called convection. Tectonic plates of the lithosphere float on top of the asthenosphere as they are less dense than the material of the asthenosphere. So think about an ice cube floating on water. The ice cube is less dense than water, so it floats around on top of the water. Convection is the process by which hot material rises and cooler material sinks. So maybe you've heard about this with air, how warm air rises and cold air sinks. That's the same is true with the mantle. The mantle is warmer near the core, and as it warms up, it rises, and then as it gets farther away from the core, it cools down and then sinks. So convection is that process where it's rising, cooling off, and falling, and warming up and rising and cooling off. Let's go back to here. Beneath Earth's surface, temperature increases with depth. Deep within the Earth, the soft material of the asthenosphere heats up and rises toward the crust. As the material gets close to the crust, it cools down. As it cools, it sinks back toward the core. Eventually, the sinking material heats up and rises again. This circular movement is called convection currents. And in this picture beneath me, you can see the arrows where you have this warm mantle rising. It's moving this way, and then, oh, now it's cooled off, so now it's starting to sink. And then it's happening here. It's sinking, and it's warming up, and then it rises again. And here's a plate right here. So you have this plate that's being pulled along right on top of that moving mantle. And some of this crust right here is sinking back down into the mantle where it will eventually melt. All right, so take out your highlighter again. I want you to highlight the words we've seen here so far. I'm going to move my face out of the way so we can do that. We have convection currents. That is what's moving the tectonic plates. And if we go down here, this is where we define convection currents, this circular movement of the mantle. And the asthenosphere is the shallow layer of mantle called the asthenosphere. And convection, when hot material rises and cooler material sinks. Okay, as you can see in the diagram up above me now, some convection currents in the asthenosphere flow in a clockwise direction, and some flow in a counterclockwise direction. As the asthenosphere flows, tectonic plates move with it in different directions. Scientists explain this process through the theory of plate tectonics. So here we have the convection currents pulling the plates with them as they move. Tectonic plates float on top of the asthenosphere as it flows. However, the asthenosphere is not actually a liquid. The asthenosphere is solid, but it has plasticity. Ooh, big science words in here. Here's another one. Plasticity is the condition of a solid that flows, that allows it to flow like dough or putty. So if you think about dough like bread dough or Play-Doh, if I hold it up here, it will begin to drop out of my hand very slowly. It's a solid, it's not a liquid, but it has plasticity. It has the ability to move. Tectonic plates interact at plate boundaries. Tectonic plates are constantly moving. At different times, some plates move faster than others. However, even the fastest plates move only tens of centimeters every year. Tectonic plate boundaries are places where the edges of two or more plates interact with each other. All right, time to get back the highlighter. This time I want you to highlight the word plasticity. Remember, plasticity is the ability to move even if it's a solid. So like Play-Doh, I can mash it. It's a solid, it's not a liquid, but I can smash it and it will move. Tectonic, those are the plates that we're studying, and tectonic plate boundaries are the places where the edges of two or more plates meet. Okay, let's talk some more about these tectonic plates. Because Earth's plates are all moving at different rates and in different directions, there are different kinds of tectonic plate boundaries. There are convergent plate boundaries. Now, here's what I want you to do. I want you to take your two hands like this. Here's one plate, here's the other plate. Now I want you to move them together. When two things come together like this, that's called converging. So you can have a whole lot of people converging on, say, Wrigley Field, or you can have two plates converging. That means coming together. So at a convergent plate boundary, where two plates are coming together, they sometimes start to overlap like this. That could be a convergent plate boundary. Or sometimes they smash together like this, and then you get this mountain range here. Those are two types of convergent plate boundaries. Now, divergent plate boundaries are, well, the opposite. So if you have a divergent plate boundary, you have two tectonic plates and they're moving away from each other like this. Now, where they're moving away from each other, there's this gap opening up here. That gap is going to fill with magma. And so you have this volcano that's created right here in a long line where those two plates are separating and magma's coming up. That's what you're looking at right here in this picture. Over there. It's hard to point to the picture when it's like the opposite of where you are. Anyway, there's the cat again. That plate boundary, here you have magma coming up in the middle and the two plates are separating. That's a divergent plate boundary. Now you also have what's called a transform plate boundary. Transform plate boundaries are where two plates are sitting next to each other and they're moving side to side, usually in one direction, but they're moving like this. That's what's happening. I'm going to scroll down here a little bit. That's what's happening in California. So you have this plate, the Pacific plate, that's right here, and then the North American plate. They're sliding past each other. So California, half of California is moving to the north, while the other half is moving to the south, which is going to be really strange someday when Los Angeles creeps up here to about where San Francisco is. But we'll all be long gone by that time. Let's go back up and read this paragraph that I missed. Below, you can see a diagram of each type of plate boundary. Remember, tectonic plates are made up of Earth's lithosphere, which floats on top of the asthenosphere. Some tectonic plates are mainly beneath the oceans, while other are mainly the continents. So here are two tectonic plates that have ocean on top of them, and there's the plate. Now here is, remember when two plates are coming together? We didn't talk about this diagram. This one is the oceanic plate is coming in, the continental plate is coming in, and oceanic plate is dense. So remember, like the water and the ice cube, the continental plate is going to go over the top of the oceanic plate. So now this oceanic plate is going down underneath, and as it goes down into the asthenosphere, it's starting to melt. Then as that plate melts, here's what happens. Some of the magma rises up to the surface, and you get a chain of volcanoes right here. Ask your teacher to show you a picture on Google Earth of the islands off the coast of Alaska. Those islands, they're called the Aleutian Islands, are actually created at a convergent plate boundary. So I think I pretty much described all the stuff that it says in there. Okay, let's take a look at this. It says, what do you think? These two diagrams show different plate boundaries. Which plate boundary does each diagram show? What do you think would be the result of each plate boundary? All right, so let's take a look at this first one. You have a continental plate coming at another continental plate, and it looks like they might be crunching up to form mountains. Okay, so it looks like those two are coming together and maybe forming some mountains. Then on this side, right over there, oh, I did it right. You have two pieces of crust, two of the plates that are moving apart. Do you remember what kind of boundary that was? Look back at your paper really quick and see if you can tell me. That's right, a divergent boundary. Okay, so let's read about recycling Earth's crust. Earth's crust is constantly being recycled. In other words, old crust is forced far beneath Earth's surface where it melts. At the same time, oh, hold on. My dog is eating my shoes. I'll be right back. Where was I? I just saved my shoe. At the same time, molten rock at Earth's surface cools and forms new crust. Older crust is melted at special convergent boundaries called subduction zones. We talked about that a little bit above. So if my oceanic plate, which is more dense, goes down underneath the continental plate, it's subducting in a subduction zone. You know how you remember that? Do you know where submarines go? They go underwater. So sub means under. So a subduction zone is where the crust goes, one piece of crust goes underneath another piece of crust. A subduction zone occurs when oceanic crust meets continental crust, or where two oceanic crusts meet. When the two plates come together, the denser of the two plates is pushed underneath the less dense plate. Oceanic crust is denser than continental crust. Therefore, at a subduction zone between continental crust and oceanic crust, the oceanic crust is always pushed underneath the continental crust. At a subduction zone where two plates of oceanic crust meet, whichever plate is denser is pushed beneath the other plate. Eventually, the bottom plate is pushed far enough into the Earth's mantle that it begins to melt. It becomes molten rock that can be recycled back into the mantle. So if you look at the picture, over there, you see the subduction zone here. And here's that magma here, where it's coming up over here and creating a chain of volcanoes. This says the circled part of this diagram shows a subduction zone. The denser oceanic crust is pushed beneath the less dense continental crust. A deep valley called a trench forms along the subduction zone. So here you have this deep valley called a trench. Can you get your highlighter back out and highlight subduction zone and highlight trench? And then let's read this little paragraph right here. The new crust, right above me, the new crust is made at special divergent boundaries called seafloor spreading centers. Seafloor spreading occurs at mid-ocean ridges. A mid-ocean ridge is made up of two long mountain chains separated by a deep valley in the middle. So remember those divergent plate boundaries where they're coming apart like this? We have magma boiling up in the center and forming little mountains. And then it moves apart again. More magma, moves apart again, more magma, you get these mountain chains. So, what do you think? Two oceanic plates move away from each other on either side of this valley, pulling the ridge apart. As the two plates move away from each other, magma rises up from the mantle in between. When the magma rises up into the valley, it cools and solidifies into new rock. This creates new oceanic crust. The formation of this new crust helps to push the two plates farther apart. Locating tectonic plate boundaries. When two continental plates come together at convergent boundaries, they push against each other. Over time, this forces the crust upward at the edges of these continental plates. This pressure can cause long mountain chains. So the two plates, remember, they're converging or coming together. They're coming together and lifting up. And where they lift up, they're creating a mountain chain. You should ask your teacher to show you the Himalayas on Google Earth. Scientists look for these landforms to help locate the boundaries between tectonic plates. The types of features that scientists find at tectonic plate boundaries can also tell them if the boundary is convergent, divergent, or transform. For example, mid-ocean ridges are found at divergent boundaries. In addition to landforms and other features, scientists can study geologic events to help locate tectonic plate boundaries. Earthquakes are particularly useful in this way. When tectonic plates push against each other at convergent boundaries or slide against each other at transform boundaries, pressure builds. Eventually, enough pressure builds up and the plates suddenly slip. This sudden release of pressure, and they go just really slow. That's what causes an earthquake. Volcanoes are another feature scientists can use to help locate and classify tectonic plate boundaries. Volcanoes are common around subduction zones, which we've talked about, right? The denser oceanic crust is sinking beneath the um, the continental crust, and where it's melting down here, that melting magma is pushing up and creating a volcano above it. The release of pressure during an earthquake can also allow magma to come up from the mantle. This sometimes results in a volcanic eruption. Looking to the future, supercontinents. The crust of Earth's continents is less dense than the crust beneath the ocean. As a result, at subduction zones, continental crust is not usually forced deep enough into the mantle to be melted. Instead, the continents move or drift across Earth's surface over time. The continents have not always been in their current locations. If you look closely at a world map, you may start to notice that some of the continents seem like they could fit together like puzzle pieces. That is because at one point they did. During several periods in Earth's history, some of the continents were so close together that they formed supercontinents. About 250 million years ago, all of the continents were connected together into one giant supercontinent called Pangaea. Pangaea means all the Earth. Do you have your highlighter? Highlight supercontinents and Pangaea. The supercontinent is just what it sounds like, one huge continent. And Pangaea was a time when all those continents were together. All the Earth was together in one huge continent. The continents are still moving today, which means that they will not always be in their current location. Maybe someday, millions of years in the future, they will come together to form another supercontinent. Take a look at this map here. Here's a map of Pangaea 250 million years ago. This is what we think Earth continents would have looked like. All the continents on Earth formed one supercontinent called Pangaea. Can you make out the continents from today? Do you see this would have been India? Here's India. And here I can see the outline of Africa. And here's Alaska and North America here. Tectonic plates interact at convergent, divergent, and transform boundaries. Read the characteristics of plate boundaries in the box below. Write each characteristic in the correct section of a Venn diagram. So I want you to take a moment to see which one of these characteristics is found at what type of plate boundary. So if you had a transformed plate boundary where two plates are sliding past each other, what sort of things might you expect? Would you expect to see floor spreading right here? No, probably not. Would you expect a mountain chain right here? Probably not. So I want you to think about, remember, transform, where they go side to side, divergent, where they're coming apart, and convergent, where they're coming together. Take a moment to fill out that Venn diagram. I hope you enjoyed reading with me, and I look forward to reading with you again some other day.